finished grading Q7. I'm gonna make the tutorial for Q7. I'm so sorry I wasn't able to make the tutorial for Q6 because anyway, this is like 2 in the morning. I'm not sure anybody. I see Raf is studying there, but everybody else I think sleeping. But I'll give it a try to finish it. The Q7 wasn't that difficult. For problem 1, 2 are the same, 3, 4 are the same, 5, 6, and 7 are the same. So the problem 1, 2 exactly the same. You keep the net force constant, then you get the what you get the, if you increase the mass, you decrease the acceleration because you're keeping the net force in. So lots of problem gonna be you're gonna see lots of problem are the same. If I can finish it, then I'll share it with you. If I'm not, then I'll go over all those problems in the classroom. Watch very carefully. This is F1, applied force. This is F2. Oh, this is F2. This is F1. Be careful. M1, F1, M2, F2. Not a big deal, easy. Now, we made a convention that positive x is east. Okay, we made a convention in the problem. I didn't have to because we already know that east is positive, west is negative. So what are we going to do? M2, so this is M2G, this is F2, this is Fn, this is Ft. Newton's second law tells F2 minus Ft. Okay, I negate it. So this is M2A. Okay, this is M2A. Now, you don't know before you solve the problem which way object is accelerating. Newtonian algebra, Newtonian mechanics will reveal that. Okay, so M1. So this is Ft, this is F1, okay, and this is M1G, and this is what? Fn. So this is Ft minus, I'm going to negate it, right? Minus F1 is equal to M1A. You probably think, how do you know this is not accelerating this way? Because it's not. It's not accelerating this way. So the object is accelerating at the same direction, right? Both objects accelerating at the same direction. And we made that we don't know before we solve the problem. The problem, once you solve the problem, you know that. Okay, so Ft is equal to M1A plus F1. And then here is F2 minus M2A is equal to Ft. So you're going to say Ft is equal to Ft. Ft is equal to Ft. So you're going to write M1A plus F1 is equal to F2 minus M2A. So M1A plus M2A is equal to F2 minus F1. Now you see that F2 is bigger than F1. You didn't see it before. Now you see that F2 is bigger than F1. Okay, so the math, Newtonian mechanics made it obvious that F2 is bigger than F1. So acceleration is then F2 minus F1 over M1 plus M2. That's the answer. So when I ask you what is the external force, external force acting on the box is F2 minus F1. That's it. And what is the mass system? And that is M1 plus M2. So when you write A is F net over M, then you write F2 minus F1 over M1 plus M2. Okay, that's very simple. But let me invite a graduate physics student at Brown University. So Raf, go ahead, show it.
Okay, two boxes A and B with masses M1 and M2 are connected by a cord and rest on a frictionless horizontal surface. Okay. Okay. A, B. They have masses M1, M2. Okay. Take the positive x direction to be the east. F2 is applied to box B in the plus x direction. Okay. F2. F1 is applied to box A in the minus x direction. The boxes accelerate together as a single system using a derivative. Okay. Okay, let's see. Oh, sorry. What was the question?
Find the external force acting on the box
Oh, find the
system.
acceleration.
Find the acceleration.
Okay.
That means you're going to find F net, right?
Mm-hmm.
What is F net and what is M system?
Okay. M system is just MA plus MB.
Okay, M1 plus M2. Okay, so first let's draw the free body diagram here for M2.
So gravity. Let me write it down. Normal force.
Why needed too many notation like this? Just M2G is enough, I guess.
Okay. Yeah.
And Fn.
Oh, it's the same thing.
Okay.
And then there's the F2 this way. And let's say this is force of A on B.
Then we're gonna call it F tension.
Okay. Or I'll just write this as F2. Okay. So that's all of M2.
Can you finish the Newton's second law here?
Yeah.
It's accelerating only the x direction, so.
Yeah. So it's gonna be
Not okay.
M2A is F2 minus Ft.
Okay, so there is no need for like the hunky funky. So you can write F2 minus Ft is equal to M2A.
Okay. Well, that's what I wrote there. F2 minus Ft
is equal to M2A.
M2A.
Okay, great. That's finished. Can you separate? Can you isolate Ft? So F2 minus M2A is equal to Ft.
Okay. F2
minus M2A is equal to Ft, because we're gonna let Ft. Okay, let's see.
and okay, M1G Fn. This is F1. This is Ft. So
Newton's second law.
yeah. So let's see. Ft minus F1 is M1A.
Now I'm gonna stop you over here. Some student probably gonna say, how do you know, Ref, that the box is not accelerating this way? How do you know why you are not putting negative over here? How are you gonna address that misconception?
Okay, so you don't know before you find the acceleration, but whatever the acceleration of box B is, box A's acceleration has to be the same.
So how do you know F2 is bigger than F1? Who told you?
You don't know, but if I find that A is negative at the end, then I know that everything is flipped.
Okay,
But
very good.
But until then, I don't know.
Very good. So one thing, if you use this one negative, then you use this one negative. If you use this one positive, use this one positive. So at the end, you figure it out whether it's moving to the east or moving to the west.
Right. The minus sign will tell you.
Minus sign will tell you.
Which one is bigger.
Very nice. Okay. All right. Finish it. Separate Ft.
Okay. Well, I can just.
No, isolate Ft.
Okay. Or you can just plug this in. You know what Ft is.
Sure, sure.
So F2 minus M2A is M1A. and then you can F2 minus F1 is M1 plus M2. Okay.
Okay.
So I can
Yeah. So the answer is now very easy.
2 minus F1 over M2 plus M1.
Okay, very nice. So then the F net, what is the external force acting on the box?
F2 minus F1.
F2 minus F1. And what is the mass system altogether?
M1
Plus M2. Okay. If I ask you a question, if I double the mass, what happened?
Just mass 1?
Yeah.
Then I'll put a 2M1 here.
2M1 over there.
Yeah.
So you mean Newton's second law hold, right?
That's right.
Which is acceleration is proportional to 1 over m, right?
Yeah.
If mass go up, acceleration go down.
Yeah.
Why?
Well, there's more inertia.
Okay, inertia doesn't guarantee that. Okay, more inertia, okay? More inertia. Because if you double the mass of the moon, the centripetal acceleration doesn't change, although inertia go up. So inertia itself cannot guarantee the acceleration go up or down.
That's right.
Inertia itself cannot guarantee. That's right. Inertia, it needs one more thing to guarantee it. Net force remains, the net force has to be constant. So although you said you add 2 over here, right? You add nothing over there. So you increases mass had no effect with the external force. External force remain constant.
That's right.
That's why Newton second law hold.
Okay. Because when you increase the moon's mass, the force also increases.
The force also increases. Acceleration is still the same. Yeah. Only inertia increase doesn't guarantee.
But when you increase the Earth's mass,
when you increase the Earth mass, because Earth is the source.
Yeah, that creates the gravitational.
That creates the field.
Yeah.
So if you change the Earth mass,
the moon's velocity will.
Moon acceleration will double.
That's right.
If you double the mass of the Earth.
Yeah.
Yes.
That's right.
Because, but yeah, that's the reason, because the Earth is the one source mass or the central mass. Right.
Yeah.
Right.
And also it's important, this rope cancels out.
The rope cancels out, okay, the
FT,
tension, yes.
FT.
Yeah, FT1,
so
FT1 and FT2 are the same.
Yeah, so this is an internal force.
This is not external force.
Yeah, and it doesn't show up.
That's right. People think that FT is external force. No, Newton's first law said, this box not happy. Why? This box always wanted to move with constant velocity in a straight line forever. Yeah. But this evil guy made it impossible for this box to move with constant velocity in a straight line. If you somehow can remove this, then this will be happy forever.
And you can double check you got the right answer. Because if F2 and F1 are the same, then acceleration is 0.
Yes, and then acceleration is 0. Right.
Makes sense.
Right, absolutely. All right, thank you, Ralph. Okay. All right, baby, you go back to your study. Thanks for clearing that up. I saw my student were okay. All right, I'll see you soon. Okay, baby. So let's go to problem number 2 now. Problem number 2, we kind of addressed the issue over there, but let's address it again. So Q7, right? Q7 we're gonna do here. Box M1. Now this is 2M1, right? Because I double the mass. And the last time you see from problem 1, external force was F2 minus F1. Okay. We'll see the external force will remain same here. What will change? This was from system M system M system was M1 plus M2. External force will remain same. You'll see that. That was the idea of today's. This is F1, this is F2. This is F1, this is Fn, this is Ft, this is 2m1, so this is 2m1g, this is F1, this is Fn, this is not, this is F1, this is Ft, this is F1. This is big careful. F1 minus Ft is equal to M2a. So F1 minus M2a is equal to Ft. Ft minus F1 is equal to 2M1a. Ft is equal to 2M1a plus F1. So Ft is equal to Ft. So 2M1a plus F1 is equal to F1 minus M2a. So let's see, 2M1a plus M2a is equal to, oh, this is F2, this is F2, this is F2, this is F2, this is F2. So F2 minus F1. So acceleration is F2 minus F1 divided by 2 M1 plus M2. So as you see that the quotient 2 external force remain the same, F2 minus F1. However, the M system went up, so 2M1 plus M2. So altogether acceleration 1 was bigger than acceleration 2 system. Why? Because both cases F2 minus F1 remain constant. However, F2 minus F1, M1 plus M2 is bigger than F2 minus F1, 2M1 plus M2. This is the summary, and I hope you understand the summary. You need to understand the summary. Before we didn't know which direction box is accelerating. Now that acceleration is positive, because this is a positive number, this is also a positive number. We know that box is accelerating to the east. I gave you problem 3 to again remove misconception that mass go up, acceleration go down if and only if net force is constant for scenario 1 and scenario 2. But problem number 3, you will see that the net force in scenario 1 is bigger than net force in scenario 2, but yet the acceleration went down. Acceleration is bigger used in scenario 1, but acceleration really went down in scenario 2, although the net force did not remain same. So no, you just cannot say that if net force remains same, then acceleration go up or down if mass changes. You just cannot say that. You have to use the Newton second law very carefully using the free body diagram. Okay, so that's the big idea for problem number 3. 2 scenario going to allow you to see okay. Scenario 1 we'll do here. Scenario 1, this is 12 kilogram, this is 10 kilogram. The box are connected by a rope. There is a mu k which is 0.1, and the box is pulled by 110 Newton at 60 degree. This is scenario 1, and this is scenario 2. I'm going to double the of course double the mass, so I'm going to do it here. 24 kilogram, right? I connected 10 kilogram, and then again everything is same. Fa is 110 Newton at 60 degree. Then you will see that acceleration is bigger over here and acceleration is smaller over here. F net is bigger over here, but F net is smaller over here. Okay, there you go. So yeah, we cannot say this is exception to the rule. So there would be 3 scenarios in. I want you to discover Newton's second law. Actually, in this quiz, I wanted you to discover Newton's second law. Okay, so let's do this one first. So 10, we're gonna call M2G. This is we're gonna call F2x. M2G is 100. F2x is 55. This is F2y is 95. This is Fn is 5. This is FF 5 times 0.1, so 0.5. This is Ft. Okay, I believe I'm done with this one. So I'm going to write F2x minus Ft minus FF is equal to M2A. I have to write 2 over here, F2F. You have to be very careful. All right, now I'm going to come over here. Let's see what happened. I'm going to write 12. So this is M1G. M1G is 120. This is Ft. This is Fn is 120. This is F1F is 120 times 0.1, 12. So I have Ft minus F1F is equal to M1A. So Ft is equal to M1A plus F1F. And I have Ft is F2x minus F2F minus M2A is equal to Ft. So we can write Ft is equal to Ft on the top, right? And then we can say M1A plus F1F is equal to F2x minus F2F minus M2A. Okay, great. So we're gonna write M2A plus M1A plus M2A is equal to F2x minus F2F minus F1F. Okay, so we see our external force. So acceleration is F2x minus F2F minus F1F over M1 plus M2. So our external force is right here. This is our external force. Okay, that's it. That's our external force. Okay, so now the second one, our external force is smaller and our mass is bigger. Okay, all right. So this is our mass. But second one, our mass would be bigger. So let's plug that in. Let's see what it is. But plugging in is not what I ask you. If you give me this answer, I'll take it. If you give me this answer, I'll take it. Whatever you give me, I'll take it. Okay, now let's do this one. 10. So 10. So this is M2G. This is 100. This is F2x. This is 55. This is F2y. This is 95. This is Fn. This is 95. This is 5. This is Ft. This is FF. 5 times 0.1, 0.5. So Newton's second law tells us exactly the same thing. This one did not change. I changed this mass. I did not change this mass. So this is f2x minus ff minus ft is equal to what? m2a. Don't forget to put 2 f2f. So f2x minus f2f minus m2a is equal to ft. Okay, now we're going to do this one. You see this one is bigger. Okay, so m1, so m1g, which is 240, this is ft, this is fn, 240, 240 times 0.1, so 24, ff1 is 24, so ft minus ff1 is equal to m1a. So ft is equal to m1a plus ff1. Okay, so now we're gonna set it to each other. So we're gonna say ft is equal to ft. So m1a plus f1 is equal to f2x minus f2f minus m2a. So m1a plus m2a is equal to f2x minus f2f minus f1f. So acceleration is f2x minus f2f minus f1f is equal to m1 plus m2. Now if you compare this one, f2x, and they look same, exactly look same, but I'll guarantee they are not the same, because we'll plug in and we'll see they are not the same. So we're going to see f2x is 55, so we're going to write acceleration is 55 minus f2f, so this is f2f 0.5, right? This is f2f, this is 0.5, so 55 minus 0.5 minus f1f. What is f1f? f1f is 12 minus 12 divided by m1 plus m2, so that's easy, 22. So acceleration is 1.93. I don't know, we'll check, double check, or why don't you double check? Now over here acceleration is f2x. Over here you see that this is the external force. Over here, what is it? This is 55. So far so good. 55 minus f2f. f2f is 0.5. 0.5. So far so good. 55 minus 0.5. So far so good. There you go. It changes. Minus 24. Minus 12. Minus 24. There you go. It changes. So external force is over here is smaller than external force over there, and of course the total mass is over here bigger. This 24 is 34, so this must be 0.9 or something. Okay, meter per second square, but double check by using calculator. My main idea, if you write this one, okay, then if you write this one or this one, you get the right answer. If you write this one or this one, you get the right answer, because this one and this one and this one and this one are the same. But if you plug in, they are not the same. Okay, so although they look same, they are not the same. That understanding going to come from you understanding that if there is a friction involved, if mass go up, the net force is not going to be the same. Net force is going to go down. Okay, so what misconception we remove over here, that the net force doesn't have to be constant for acceleration to go down when mass go up. And here is the example. You're going to get point if you get this one or this one. You don't have to write both because they look the same. 5 and 6 are the same problem, if you realize. Okay, so first let's start with problem 5. Problem 5 has 3 part. Problem 5 has 3 part. Part 1, the finding the acceleration of the moon due to the earth. So here is the diagram. This is moon moving counterclockwise. This is earth. You're gonna find the acceleration of the moon due to earth over here, right? This is AC. The velocity is, of course, the perpendicular with respect to the AC. You're going to find the AC acceleration. Okay, so how are we going to find it? You're going to write FG is equal to mg, G, big M, small m over R square. So mg is equal to big G over R square. So this cancel. So G is equal to big G M R square. What type of G? Acceleration. Okay. G is 6.67 times 10 raised to negative 11 Newton meter square over kilogram square. M is 6 times 10 raised to 24, right? And radius, the radius is 3.84 times 10 raised to 8 square. So then AC is 6.67 times 6 meter square. 6 divided by 1.5 times 10 raised to negative 11, positive 24, minus 17. Okay, so AC is this is 27 times 10 raised to 24 minus 28 minus 4. So you're going to say AC is 2.7 times 10 raised to negative 3 meter per second square. Now what happened? We're going to double the mass of the moon. Okay, if you double the mass of the moon new moon gonna look like this. All right, we double the mass. What happened? Let's see what happened. That's scenario number 2. Even if you double the mass, this M cancel. Even if you double the mass, that is still smaller than the earth. So the B small mass doesn't really small mass cancel, because it's still the moon, even after you double it, is still 40 times smaller than the earth. Okay, so G is same thing, G big M over R square. So then what type of G? Acceleration. What type of acceleration? Centripetal acceleration. So 6.67 times 10 raised to minus 11, 6 times 10 raised to 24, and then 3.84 times 10 raised to 8 square, and that gives you the same thing, 2.7 times 10 raised to minus 3 meter per second square. All right, now let's see, we're going to double the mass of the earth. Okay, we're going to double the size of the earth. So we're going to doubling the size of the earth. The moon is moon. So moon is 7.35 times 10 raised to 22 kilogram. Earth is 6 times 10 raised to 24 kilogram before. Now we're going to double it, and we're going to see what happened to the acceleration of the centripetal acceleration of the moon due to earth. So of the moon due to earth, we're going to find this one. Okay, this is earth. Okay, so mg is equal to m G big M small m over R squared. So these cancel anyway because it was already big. Now it's even bigger. So what type of G? Acceleration. G is 6.67 times 10 raised to negative 11. M is now twice. So it used to be 6, now it's 12. 12 times 10 raised to 24. And then is 3.84 times 10 raised to 8. That's the distance between Earth to the moon. Radius. Okay, you get it. All right, so you have 6.67 times 12 divided by 1.5 times 10 raised to negative 4 meter per second square. So this is 5.4 times 10 raised to negative 3 meter per second square. Scenario 1 give us 0.003. Scenario 2 give us 0.003. Now scenario 3 give us 0.006. All right, so yeah, you see doubling, almost doubling, right? Almost doubling. Why? Because I want you to discover this. Acceleration is proportional to the mass. What? We thought acceleration is inversely proportional to 1 over mass. Well, in the sky, acceleration is proportional to the mass. And that is what takes us to problem 6, because 5 and 6 are the same problem. You solve one problem, but you get the credit as if you're solving two problems. Okay, so let's see how this is true. And that takes us problem number 6. Prove that this is true. How can you prove that? You start with hamburger is equal to hamburger. You can write, I don't know, FC is equal to G big M small m over R square. FC is M V square R is equal to G big M small m R square. So what are you trying to prove is this one. So small m cancel. So V square over R is AC. So AC is G M over R square. So then AC is proportional to M. Is proportional to M. 7 is also part of 5 and 6. How is that? A few seconds ago we discussed about, we actually proved that. Now we're going to discuss a little bit more about it, because so just like 5 and 6, problem 7 is part of them. When you say Newton's second law, and when you say gravitational circular motion, okay, so what is the main hypothesis over here? The main hypothesis is acceleration is proportional to 1 over mass. What is the main hypothesis over here? We just proved that acceleration is proportional to mass. You can write central. A few seconds ago I showed you proof. Problem number 6 you saw the proof. Now problem number 7, you try to understand why this is the way it is. And when this is true when net force, when F net is constant, in a body in a frictionless surface. So then you cannot say that 3 and 4 is an exception. No, 3 and 4, the F net wasn't constant, but mass go up, acceleration go down, is because there is a friction. If there is no friction, then if net force not same, then even mass go up, acceleration will not go down. Net force has to be constant for acceleration to go down if mass go up. So let's go over number 8 quickly. So number 8, scenario 1, I gave you an inclined plane, 30-degree angle, a box sitting here, and mu k is 1.1. So you have FG parallel over here, you have FF over here. So FG parallel minus FF is equal to MA. So mg sine theta minus mu k mg cosine theta is equal to ma. M cancel, g sine theta minus mu k g cosine theta is equal to acceleration. So acceleration is equal to g sine theta is 5 minus mu k is 0.1 times 10 cosine 30. So acceleration is 5 minus this 1, so 0.87. So acceleration is 4.3, 4.4, something like that. Okay, now this one, you have a box, 2 kilogram box is roping with M2 hanging. What should be M2 so that this acceleration is also 4.3? Okay, so M2, you have M2G, you have FT. So Ft minus M2G is equal to minus M2A. So then Ft is equal to M2G minus M2A. Okay, let's do this one. This is Ft, this is FF. Okay, so Ft minus FF is equal to M1A. So Ft is equal to M1A plus FF. Okay, so we're gonna let this to each other. So MA, M1A plus FF is equal to M2G minus M2A. So M1A plus M2A is equal to M2G minus FF. So A is equal to M2G minus FF is equal to M1 plus M2. And that is M2 is, we don't have it, so we're going to write it, M2G is 10 M2 minus FF. FF is mu k mg cosine theta. So mu k 0.1, m is 2, g is 10. Oh, what are you doing? FF is just mu k mg. FF is just here FF. FF is mu k Fn. Okay, so mu k is how much? 0.1. Fn is how much? 20, right? This is 20, so this is 20. So Fn is 20. So this is 2. FF is 2. Okay. So 10m2 minus 2 over m1 plus m2. m1 is 2 plus m2. And that is equal to 4.3. Okay, so 4.3, we're going to cross multiply. 10m2 minus 2 is equal to 4.3 times 2, so 8 times 8.6 plus 4.3 m2. Okay, so 10 m2 minus 4.3 m2 is equal to 8.6 plus 2. So you have m2 is 1.7 or 1.8 kilogram. So that the both acceleration is 4.3. 9 and 10 are very easy because number 9, I give you the jumping problem again. So location A, B, C, the A, y is negative 0.2, B, y is 0, C, y is 0.8. You crouch for 0.2 meter, your max height is 0.8. Here velocity is 0, acceleration is 0. Here velocity is 0, acceleration is g. Here you have to find the velocity and acceleration. Okay, the man is 100 kilogram. I want you to find the man acceleration when he is about to leave the ground. There's scenario 1. Scenario 2, the man is now double. Everything is same. A, B, C. The man is now 200 kilogram. You have to find the man when he jump up, his acceleration. So both of them you're going to find in the acceleration. Find the acceleration, you have to find the velocity first. Vf square is equal to vi square plus 2ad. So this is vc square is equal to vb square plus 2 gd. So 0 bb square plus 2 negative 10, and that's 0.8. So vb is 4. So again vf square is equal to vi square plus 2ad. Now this one would be vb square is equal to va square plus 2ad. So this is 4 square is equal to 0 plus 2a. This is 0.2. So acceleration is 40. Same here, acceleration is 40. Why? Because nothing will change. There is no formula where you can plug in the mass. Okay, so here the force increases, the force go double. That's why the acceleration remains same. The force did not remain constant, and the very classical Newtonian second law clearing up misconception. Here, what is the force? Fn. Fn is double now. Fn is mg plus a. So Fn is 100, 10 plus 40, so 50, so 50, so 5,000 Newton. I believe this is 10,000 Newton. Fn is equal to mg plus a. So 200, mass is 200. 200 g is 10 plus 40, 50. So 200 times 50. 10,000. Okay, so Fn go double. Okay, so that's why the acceleration remains same. The elevator problem, which is easy, scenario 1. All right, so scenario 1, you have a counterweight and you have a weight. So this is 1,000 and this is 3,000. Okay, I believe, I don't know, this is 3,000, this is 5,000, I don't know, let me see. The first one 3,000, 5,000, 3,000, and second one 10,000, 3,000. This is 3,000 and this is 5,000, and this is, we're gonna double the mass. This is 3,000, this is 10,000. Okay, so we are trying to see, will the acceleration gonna be the same? No, acceleration not gonna be the same, because the force will not go double, right? Force will not go double. So acceleration will not be, will the force remain constant? We'll see. Okay, so let's see. Acceleration is big M minus small m, m1 plus m2. This is g. So acceleration big M, this is your external force. Big M is 5,000 minus 3,000, so 2,000 times 10. This is 8,000. Okay, so external force is, you see, 20,000. Let's see. External force is 2, 1, 2, 3, 4. 1, 2, 3, 4. So 20,000. 1, 2, 3. 1, 2, 3. Okay, 8 goes to 20. 2.5, I believe. Meter per second squared. Okay. All right. So we saw that 20,000 is the external force. External force is 20,000. External force is 20,000. In this case, we'll see whether external force is 20,000, but we know that the acceleration will go up. Acceleration will go up. We'll see. Acceleration big M minus small m divided by m1 plus m2 multiplied by g. Big M is 10,000 minus 3,000, 7,000 times 10, 13,000. So acceleration, right, so here 1, 2, 3, 4, 1, 2, 3, 4. So here 70,000. Geez, 70,000. This is 20,000, more than double. Okay, so of course the acceleration will increase. 1, 2, 3, 1, 2, 3. So 5 point, I don't know, 5.2, 5.36, anyway, 5.3, whatever it is. The idea is over here, acceleration went up. Why is that? So in this case, the mass go up, acceleration also go up, is because the force go up more than double. So last two problem, 11 and 12. Let's see. 11 is another problem when you have mass go up, acceleration go down, because it has to do with friction. So 11. Okay. Let's see. Okay, so first we're going to do with 6 kilogram. So 6 kilogram object, and you have 60 Newton, 30 degree, mu k is 0.2. You're going to double it and see how that changes the acceleration. 30, 60 Newton, mu k is 0.2. All right, you have 60 Newton. You have 60 cosine 30, I believe 52 Newton, 30. So FF is 30 times 0.2, 6 Newton. So F equal to MA in the X direction. 52 minus 6 is equal to M is 6A. So A is equal to 52 minus 6 is 46. 46 divided by 6. So acceleration is 2. Let's see. 7.7, I believe. Okay. All right. Now let's see this one. This one definitely gonna be smaller than this because I double the mass. Okay. So yeah, it's the same thing. 120 Newton, 52 Newton, 30 Newton, and this is 31 Fn is 90 Newton, 90 times 0.2, 18 Newton, which is friction. So 52 minus 18 is equal to m. M is 12. So A is 52 minus 18 divided by 12. 52, so 34 divided by 12, that is 22.8. So this is 2.8. So let's verify this one. 52 minus 6, that is 46 divided by 6, 7.7. Yeah, that is correct. Okay. So what do we see? That the external force, they are not the same. External force decreases, that's why acceleration decreases. So mass go up, acceleration go down. A typical case of Newton's second law, but that's not always going to hold, right? Last problem is I gave you mass, you double the mass, you half the acceleration. That's what happened. This is like a no friction, that's why. No friction, and if there is no friction and there is a constant net force, then mass double, acceleration half. Okay, 2. Okay, so mass 1, mass 2. I'm going to apply 20 Newton to mass 2. I'm just applying, pulling it down by 20 Newton. So what is it? Acceleration is F net divided by m system. So acceleration F net is 20, m system 2 plus 2 is 4. So acceleration is 5 meter per second square. I'm going to double the mass. 4. Okay. So then let's see what happened. Acceleration is F net divided by m system. F net. I'm going to pull it down by same constant force, 448. So acceleration is, I believe that has to be 2.5 meter per second square. Why? If there is no friction, then this is what it is.